Good afternoon, everybody. You heard about accelerators and many different types. And now I'm going to talk to you about a very special accelerator, a cosmic accelerator, which is gravity. Well, when we talk about gravity, you know we are talking about one of the four fundamental forces. We have the strong force, you know, which holds atoms together, no? Overcoming the repulsion of positively charged protons from each other. Then you have the weak force, which causes the beta decay and allows for the buildup of radioactive isotopes and thus the creation of something like deuterium, which helps the sun burn. Then you have the electromagnetic force, which is responsible of the, for example, no, the static electricity to hold stay a balloon on a wall, or the force that make magnets attract or repel each other. And then we have gravity, which holds you to the planet, holds the planet to the sun to the galaxies to the, which holds the galaxy together, so on and so forth. And gravity, you may know, is the weakest of the four fundamental forces. A rocket, but also a balloon, can overcome the gravity. And the Earth is gigantic in comparison with me, but I can defeat gravity right now. So the four fundamental forces have something in common, but something very different. The strong and the weak interaction, for example, are so-called short-range forces. They are active at the atomic scale. On the other hand, the electromagnetism and the gravity, they are long-range forces. They are active also on very long distances. The gravity of the Earth, of the Moon, of the Sun is acting on us right now. There is, nevertheless, a fundamental difference between electromagnetism and gravity. And this comes from the fact that in nature we have positive and negative charges, but we do not have negative masses. The consequence is that the electromagnetic force, the electric, let's say, the electric interaction can be attractive or can be repulsive. And if you have an object which is typically electrically neutral, it is quiet from the point of view of the electric interaction. Instead, gravity is only attractive, and it attracts matter and matter and matter. It never stops. This is a fundamental feature of the gravitational interaction. And we can say that even if on atomic nuclear scale gravitation is not so relevant, it becomes fundamental, really fundamental, when we consider the universe. So when we consider how the universe behaves, when we consider stars, when we consider planets. So when we talk about gravity, for example, it is gravity that determines the life, the birth, the life, and the death of a star. And as you may know, stars are born in the dark patches of nebulae, and this is the so-called cone nebula. And these are clouds, cool and dark clouds, which move slowly. And for this reason, the gravitational attraction between particles in the cloud can overcome their random movements and produce a contraction of the cloud. And as the gas cloud contracts under the force of the gravity, then the compression raises the temperature of the core until it reaches several millions degrees Celsius. And at this temperature, the nuclear reactions begin and the star is born. And you see here the massive stars determines the color, the size, the temperature, and the hottest stars go from red, yellow, white, and blue. Blue stars produce a huge amount of energy. And the source of energy that makes the stars shine is a nuclear reaction involving conversion of mass to energy. And that this is possible was first realized by Albert Einstein, as it is expressed in this famous equation, E equal mc squared. It means that a small amount of mass, m, can be converted into a huge amount of energy, E, and C is a constant, it is the speed of light. And the reactions within a star involve the fusing together of atomic nuclei. And the basic nuclear fusion reaction is the conversion of 4 hydrogen atoms into 1 helium atom. And this conversion involves a loss of a small amount of mass, a large amount of energy. And if we consider, for example, our sun, which is an average size star, this will keep on fusing hydrogen into helium for around 10 billion years. If we consider more massive stars, they burn their fuel more quickly and have typically shorter lives. And small stars live instead longer than the sun. But when the hydrogen in the core is exhausted, then a period of instability begins, and the star that can no longer burn hydrogen starts building heavier elements by fusing helium atoms together. And all these reactions take place at much higher temperatures at the core of the star. And these higher temperatures make the star expand to many times the original size, and the outer layers of such a star becomes cooler as they get farther from the core, and so the temperature, the surface temperature drops, and the star turns red. And this is what we call a red giant, which is a very large and bright star. And this is Betelgeuse, which is one of the largest stars known, with dimensions about 2.5 times the diameter of the Earth's orbit around the Sun. It's really a huge object. And these red giants, again, undergo periods of instabilities, and in which the output pressure throws the material into space, forming a nebula around the star. And so what happens at the end of the life? Well, after the star has lost some of its mass, has exhausted the nuclear fuel, it will collapse under the action of gravity, and it will form a white dwarf. The size is not much larger than the Earth, but it is very dense. A tablespoon weighs about a ton. And it can appear white, but also blue, because the surface temperature is very, very high. Now, this evolutionary pattern applies to a medium-sized star as our Sun. But if we consider higher masses stars, then the end is even more dramatic because the star will die with an explosion, which is called supernova. And here you see the remnant of this, or one of these supernova, the Vela remnant, and this is another remnant of another supernova explosion, very well known, the so-called Crab nebula. This was discovered by the Chinese astronomers in 1054, and at its center then was discovered a very peculiar object which is known as pulsars. It is a star formed by neutrons, neutrons only. Well, the innermost structure of a neutron star is actually not well known, but what happens is that the force among neutrons prevents a further collapse of the star. And you see it behaves as a lighthouse because there are huge magnetic fields, and the particles accelerated by these magnetic fields emit radio waves in a cone, and when the star rotates and the cone points towards us, we see a pulse. This is why they are called pulsars. The size is not much larger than the Earth. The mass is of the order of the Earth, but the size is much smaller, about 10 kilometers. And so they are very, very dense objects. A tablespoon, in this case, weighs about 10 million tons, okay? But if we consider stars of even greater mass, then there is no force that can prevent the total collapse, and it will become a black hole. The black hole is so small and so dense that nothing at all can escape, not even light. This is why they are called black hole. And they are the densest objects that we know exist in our universe. Till now, they have been detected by the radiation emitted from matter spiraling into the black hole as from a companion star in a double system. Some months ago, we discovered black holes through a different messenger, but I will come back to this in a while. Now, you see, we are talking about stars, we are talking about our universe, and you have seen that many violent phenomena, essentially driven by gravity, happen in the universe. Now, the question for us is, how can we study our universe? How we can investigate what happens in the universe, what happens in the star? Well, traditionally, you know, we have looked at the sky, studying the light emitted by the astronomical objects. Starting from the beginning of modern astronomy, in the 17th century, when Galileo, for the first time, looked at the sky with his telescope, starting from then, we have explored the universe through the electromagnetic radiation. And the pristine Galileo telescope has evolved into very beautiful and sensitive instruments that are currently mapping almost the entire universe. But besides the visible light, we have been exploring the universe through the electromagnetic radiation emitted all over the electromagnetic spectrum. And the keywords are map the universe in all the accessible wavelengths. So with the radio waves emitted with the microwaves, with the infrared radiation, with the X-ray, gamma ray, up and down to the gamma ray burst, this violent phenomena. Why this is necessary? Because studying the universe through different observational channels can increase our understanding of the physical phenomena. So it was very important. Our present knowledge comes mostly from the study of the electromagnetic radiation all over the accessible wavelengths. But we can ask ourselves, do we have anything else to study what happens in the universe? Do we have anything else at our disposal? And the answer is yes. For example, we have neutrinos as well. You heard we have nuclear reactions taking place inside the sun, and these nuclear reactions produce neutrinos. And neutrinos are indeed the signature we have to say that there are nuclear reactions inside the sun, not the light, which is instead emitted by the outer regions. So if we want to study what happens inside, we have to detect neutrinos. There are a lot of neutrinos coming from the sun. We have a huge flux, a huge amount of mass per second, which becomes energy and neutrinos in the sun. And the flux of neutrinos is very, very high. And if you put your thumbnail this way, each second you have 60 billions of neutrinos crossing the surface of your nail. So this is really a huge flux of particles. Now, we do not have neutrinos only produced inside the sun. We also have neutrinos during the supernova explosions. We said they are violent processes. There is a huge amount of energy emitted on a very short time scale. In the case of a supernova explosion, the typical time scale is of the order of 1 second, even shorter than 1 second, but only a tiny fraction of this energy goes into the electromagnetic radiation. Almost all the emitted energy goes into neutrinos. 99.9% of the emitted energy goes into neutrinos. And this is a picture that I have already shown you. This is the Crab Nebula. You see some of the features of this supernova remnant. It was observed by the ancient Chinese astronomer. It was also seen in America. And it was visible also during the day for 23 days. The result of the explosion, the supernova, was visible. The light curve emitted is so bright that the star could be seen by eye also during the day. And in fact, in the original engraving by the Chinese astronomers, you can read that a new star is born at east, like a celestial guardian, and the star is so bright during daylight as the polar star is during the night, with a particularly bright and white corona for 23 days. So you can imagine how violent the process is and the amount of energy which is emitted. And this is another picture of a more recent supernova, the supernova 1987A, and this is the year when it took place. and a radio-optical X-ray and gamma-emitting pulsar associated with this supernova remnant was found in the constellation of Vela, and it is called as, in fact, the Vela remnant. And it's one of these pulsars that I have told you before. Now, how can we detect neutrinos? They interact very, very weakly with matter. So they are very elusive, but they are also very penetrating. So it means that they are a very good tool to investigate the innermost regions of a star because they can escape from the star very easily. And so they can tell us, for example, about the dynamics of the collapse, what happens inside the star during this supernova explosion. But it is also clear that we need to shield very well our detectors, for example, from all the other possible particles, radiation, coming from the universe, for example, from the cosmic rays. Otherwise, the effect produced by our neutrinos in the detector could be completely overwhelmed by the interaction of these other particles. So we need typically underground detectors, and we have in Italy a beautiful laboratory, which is the INFN Gran Sasso laboratory, the lab of the cosmic silence, and where the rock of the mountain can shield very well our instrument, and we can detect the presence of these neutrinos, the interactions of these neutrinos. And these are a couple of pictures of two detectors, Borexino and LVD, located in the Gran Sasso laboratories. Borexino, for example, has about 1,300 kilograms of liquid, a special liquid which is called scintillators, and the neutrinos during their reactions produce this light, which is detected by these detectors, so they measure the light produced by the scintillation processes. Okay, we also have neutrino detectors, which are underwater, the kilometer cube net. We have detectors under ice, as ice cube, located at the South Pole. So we need some shield. It can be the rocket of the mountain, it can be the water, it can be the ice, but we need to shield our instrument. And at the end of last century, the neutrino astronomy began, and we started using also neutrinos to investigate the universe. Now, we see the light emitted from the stars, the neutrinos, anything else? Well, starting from 1 year, let's say, we can say yes, we have another tool, we have another messenger coming from the universe that now we are able to use, and they are gravitational waves. Gravitational waves were predicted by Albert Einstein within his general relativity theory about 100 years ago. And they are in practice the consequence of the presence of mass in the structure of the space-time. According to general relativity, the geometry of the space and the flux of the time are determined by the presence of matter. So you can imagine the space-time, the three special coordinates and the time coordinates as a structure, a dynamical structure, which is influenced by the presence of matter. mass changes the geometry of the space. It generates a curvature in the space-time. And so the motion, for example, of the planets around the sun can be explained because the mass of the sun deformates the fabric of space-time, and the Earth orbits the sun due to the deformation of the space-time. And if you have objects which move and accelerate, well, they produce ripples in the fabric of the space-time, and these ripples are what we call gravitational waves. They are waves of gravity. So they are produced where the mass, the source of gravity is placed, and then they move in the universe, they propagate from the source, traveling in the universe at the speed of light. They can be emitted in many of the processes we have considered. Sorry, it's not working. Let's see if we can make it start. No, it's not working. Well, they can be produced in a supernova explosion. So we have production of light, emission of neutrinos, and we also may have generation of gravitational waves. And they are very interesting because, as neutrinos, they interact very, very, very weakly with matter, even less than neutrinos. A wave crossing the Earth is unaffected by the presence of the Earth. The Earth is transparent to gravitational waves. So it means that they can travel very long distances in the universe without being affected, substantially affected by the interstellar medium, for example, by the astronomical objects that they meet during their travel. And this is very important because traveling long distances means also coming from the past. So studying the gravitational radiation, we can also get information on the pristine instance of life of our universe. That's a unique feature of gravitational waves. By studying the so-called stochastic gravitational wave background, just to mention it today. So neutrinos and gravitational wave can escape from the innermost regions of the star. They can bring us information about the structure, the internal structure of the star. Instead, light is typically coming from the outer region of the star. And so you see that how these different messengers can bring us different pieces of info to, let's say, to build our puzzle and to understand all the physical processes behind. We may have emission of gravitational waves also from pulsars, from these spinning neutron stars. If there is some asymmetry, we do not have only emission of radio pulses, but we may have also emission of gravitational waves. We may have emission of gravitational waves from binary systems when we may have two objects, two compact objects, typically neutron stars or black holes, and they spiral each other, they orbit each other, they spiral, and during this spiraling phase, they lose energy through emission of gravitational wave, and the consequence is that they accelerate more and more. So gravity makes the two objects accelerate more and more, and they get closer and closer in spiraling, and at the end of its life, this binary system will collapse. The two objects will collapse, and will form the final object that is typically a black hole, or in some cases, a new neutron star, more massive neutron star. And during this process, you have these two very, very dense objects which are accelerating more and more, and they emit stronger and stronger gravitational waves. Then, this is the case of two pulsars, for example. This is a binary system made of two pulsars, which you see orbit one each other, and they do not emit only their radio pulses, but they also can emit gravitational waves. Or you may have a binary system made by a black hole here, and you may have a star orbiting the black hole, and during this INSPYRE phase, the star will be disrupted by the gravity of the black hole, and at the end it will be eaten by the black hole. There are many binary systems in the universe, made by white dwarfs, neutron stars, black holes, mixed systems as well. So black holes, neutron stars. And the masses of the black holes can range from stellar mass objects, which means some solar mass, up to the so-called supermassive black holes, 1 million, 10 million solar masses, huge objects. At the center of our galaxy, there is a supermassive black hole, and this is typical of many galaxies. And you may also have mergers of galaxies. So, now, question is, new question for us, how can we detect gravitational waves? We know how to detect light, we know how to detect neutrinos. How can we detect gravitational waves? Well, we said that gravity waves distort the fabric of the space-time. It means they change distances between objects. And for example, here you can see the effect of the gravitational wave traveling this way, you see, on a ring of test masses. So you see the shape of the ring changes at the distances between the test masses change with a typical pattern that we call quadrupolar pattern. So in one direction the distance increases, in the perpendicular direction the distance decreases. Okay, so we can now understand how to detect gravitational wave. And the guy that you see here is Rainer Weiss, one of the Nobel Prize laureates. They have been awarded for the first detection of gravitational waves and also for the theoretical and experimental studies that brought us to understand the physics and to build the instruments to detect these signals. How does the instrument work? You have here a laser, so the laser beam is here. Then you have a mirror, which is called beam splitter, because it splits the beam in two components which travel perpendicularly one each other. They reach two mirrors, one here, one here. They are reflected. They come back. They recombine here at the beam splitter, and the overlap of the two beams is detected by a sensor here. So here we detect the light coming from the interference, from the overlap of the two beams. And if you remember the effect of the gravitational wave, which stretches and shrinks the space-time this way, then you understand that when a gravitational wave interacts with this detector, which is called Michelson interferometer, the consequence of the interaction is a change in the length of the arms. One gets longer, one gets shorter at different times. Now, in this case, I have greatly exaggerated the effect because the real displacement of these mirrors is much smaller, as we will see. So let's see better in more detail what happens. You see the beam coming from the laser, and you see the effect of the gravitational wave, and we can see now better. This is the electromagnetic wave in one of the two arms, which is reflected by the mirror, comes back, and the same happens in the perpendicular arm. The two waves recombine here at the beam splitter, they overlap, and the experimenter typically sets the length of the arm so that we do not have light. But when the gravitational wave arrives and changes the length of the arms, you see the overlap of the two electromagnetic waves changes, and we have dark and bright spot here. And this change in the light collected by the photodetector is the indication of the interaction of the gravitational wave with my interferometer. The problem, the experimental problem, is that the change in the length of the arms, and remember, I didn't tell you, but the arms of our instruments are 3-4 kilometers long, but the displacement of the mirrors, so the change in the arm length, is of the order of 10 to the minus 18 meters, over 3 kilometers. And you know 10 to the minus 18 meters is a really tiny quantity. You cannot even imagine it. You can understand how small it is if you start from a meter that you can visualize easily, and then you divide by 10,000 and you get the thickness of a human hair. And then you divide by 100 and you have a bacterium. Then you divide by 10,000 again and you get to 10 to the minus 10 meters, the dimension of an atom. You need 8 orders of magnitude more. It means that when we measure 10 to the minus 18 meters, it's as considering an atom, but you have to go deeper into the atom. You reach the nucleus, and we are 10 to the minus 15 meters. It is not enough. You have to measure 1/1000th of the dimension of a proton. This is the measurement that we have done. That was an experimental, a technological challenge. Many in the scientific community thought it is unfeasible. These crazy guys will never be able to measure gravitational waves. That was an incredible achievement of technology, of science in general. So we need sophisticated instruments to do that, and here you see one of the interferometers now built. And you see the long arms, 3 or 4 kilometers long. This is the central building where you have the beam splitter, where the beams recombine. And in the arms, the beam travels under vacuum. So they are pipes under vacuum with very sophisticated optical systems. These are the mirrors, very special mirrors, and all the technology has to be pushed at the limit. Some of the technology did not exist when the construction of these instruments started some tens of years ago. And here you can see, for example, another picture of the mirror. You see how scientists work, because all the environment must be very, very clean. The mirror cannot be polluted by dust or contaminants present typically in the air. And you see one of the mirrors suspended. These are the so-called super attenuators. They are towers, some meters high, which suspend the mirror in such a way that even if the Earth vibrates, and the Earth always vibrates, and we have seismic waves always traveling, the mirror cannot move. You understand? We have to measure a displacement 10 to the minus 18 meters. We cannot put the mirror simply lying, sitting on the Earth. We must suspend very carefully to keep it quiet in the absence of the gravitational wave. And we have very, very complex optical systems, and this is the vacuum pipe, 3 kilometers long. These instruments are the largest vacuum systems in the world. We have a network, an international network of gravitational wave interferometers, 2 in the US, LIGO, one at Livingston in Louisiana, one at Hanford in the Washington State, and then we have Virgo in Cascina, close to Pisa. And these 3 interferometers are the largest interferometers built. And then we have some more projects in India, in Japan. They are being built, but not yet in data taking. So what happened September 14, 2015? The LIGO interferometers had just started their data taking after many years of development. And at that day, that time, the output of the interferometer, which is typically, let's say, a noisy output, because we typically have noise if we do not have a gravitational signal, then this noisy output suddenly started showing a pattern. You see a sinusoidal pattern that was increasing in amplitude and in frequency in time till a maximum reached here, and then a sort of ring down. So the oscillation was decreasing in amplitude after its maximum. And that's the signature of a typical coalescence of a binary system. Because what happens when you have, for example, 2 black holes that are orbiting each other in a binary system, and you see here the 2 black holes, and you see also below the structure of the space-time, you see the deformation of the space-time, and you see here where the black holes are located, you have a huge deformation because these are incredibly dense objects, and so the fabric of the space-time generates a huge curvature. Then you see what happens. The 2 objects moves faster and faster, they get closer and closer, and you see here below the signal emitted. This is the gravitational wave emitted, the shape emitted during the inspiral up to the collapse of the two objects, and then you have seen the ring down, the last oscillation of the space-time after the production of the final black hole. So the signal that you have seen, the waveform that you have seen has been computed theoretically from the general relativity. So that is the signal that we expected to see. And what I have shown you before is that sinusoidal waveform increasing in amplitude and in frequency was what we saw experimentally, so similar to the theoretical waveform that I have just shown you. And that was the first experimental evidence of the detection of a gravitational wave produced by two black holes, colliding black holes. The initial mass of the two objects was about 36 and 29 solar masses. The final mass was 62 solar masses, so 62 times the mass of the Sun. And you see that if you sum together these two numbers, there are 3 solar masses missing in mass. And 3 solar masses in mass have been converted into energy through the equation that we have already seen. And that was a huge amount of energy. This cosmic accelerator has produced a huge amount of energy that went into gravitational waves, and that was 50 times the light emitted by all the stars in the universe, but in few tenths of seconds. So you can imagine the amount of energy involved in the process. And the distance of this source was 1.3 billion light years, so very, very distant from us. But thanks to the property of the gravitational waves to interact very weakly with matter, they could travel in the universe and they could reach the Earth and our instruments, and we could detect them. Now, one very interesting thing I want to underline is the following. We are talking about cosmic accelerators. See what happens. So this is the waveform computed, and this was the green curve. You see, this is the time. So all the process lasted fraction of seconds. So you see, and you see the velocity, the relative velocity of the two black holes. Here on the left, you see on the y-axis the velocity expressed in unit of c. So 0.5 means 1/2 the speed of light. So the relative velocity of the two objects increased, and you see at the end, this is when the two objects merged to form the final black hole. At this point, the relative velocity was higher than 0.5 c. So was higher than 1/2 of the speed of light. Objects 30 times the mass of the Sun moving at 1/2 the speed of light. That's incredible to realize. Okay, so that was the first source we detected, but we have seen more with different waveforms emitted, but the shape is similar. The duration is different depending on the mass. In fact, it is the mass of the objects involved which determines the evolution in time of the amplitude and of the frequency emitted, and you can see that lighter is the mass of the two components, the binary system, and longer is the signal that you can detect. So the lightest one was 14 and about 7 solar masses, and the duration of the signal that we could measure in this case was roughly 1.5 seconds. So now the landscape of known black holes is changing, and you can see clearly this in this plot. In purple, you see the black holes that were known before the discovery, the detection of the gravitational waves from X-ray studies, so from the electromagnetic radiation emitted by the matter spiraling the black hole. And you see the masses of these objects were typically below 20 solar masses. In this scale, you see the mass of the black holes in units of solar masses. Instead, the objects that we could detect had much larger masses, 30, but 60 times the mass of the Sun, so much heavier objects. They were completely unknown before. Scientists didn't even imagine that this type of black holes could exist, and it is not evident at present how these objects can form in the universe, how such large objects can be produced in the universe. That's an open question. We have detected gravitational waves coming from black holes, but not only from black holes, also from neutron stars. And in particular, on August 17 last year, the three interferometers, the two LIGO in the US and Virgo in Kashina, they detected the gravitational waves emitted by a binary system made by two neutron stars, not two black holes. So imagine the source is located here, then the gravitational wave is produced, it propagates out from the source, it travels the universe, and it reached the three interferometers, you see, and it was detected by this network of gravitational wave interferometers. So we had a network of interferometers to detect gravitational waves, but we also had a network of electromagnetic observatories to detect, if any, also the electromagnetic radiation emitted during the process, because as I told you, investigating the process through different messengers, through different observational channels, can give us a huge amount of information, much, much richer. And this is the case, as I am going to tell you. So what we saw is the following. Two neutron stars orbiting each other, accelerating more and more, deforming the space-time, producing gravitational waves, merging, and at the end, producing also a burst of electromagnetic radiation, a gamma burst, and then electromagnetic radiation in many different bands. So this was important, and that was an example of a fruitful cooperation between many, many different research groups. With our instruments, with the gravitational wave interferometers, we were able to say, hey guys, something is happening. We have two objects that have been merged. And Since we had 3 instruments, we could point the source. We could tell the astronomers the source of this signal is there. Look at there. You might see something with your telescopes. And so 93 groups, 93 more than 200 instruments have signed in the past some memorandum of understanding with LIGO and Virgo, the so-called LBC, LIGO and Virgo community. They signed this MOU to perform an electromagnetic follow-up. So the idea is the gravitational wave interferometers give us a trigger. Hey guys, something is happening. They give us the direction, so the position in the sky of the source, and we point in that direction and we follow up the event to see what happens in the electromagnetic channels. And all this process has to be performed on a short time scale. Shortest is the delay between what we see and the trigger that we send out, and better the astronomers can follow the evolution of the process from the electromagnetic side. So the campaign was very, very fruitful, and this is the celestial sphere, let's say, and this is the region where the 3 gravitational wave interferometers identified the source of the gravitational wave. You see, it's not a point. There is some uncertainty in the determination of the direction, but it was not so large uncertainty, and so the astronomer could look at that region of the sky. And if you compare these 2 images, the bottom one was taken about 20 days before the event, and you see here there is nothing. And here you see there is a new object, and that was the object formed by the coalescence, by the merger of the 2 neutron stars. The process is known as kilonova, is something similar to a supernova with a different energetics. That was modeled before, but nobody was able to see. That was the first experimental observation of a kilonova. And it was observed in the gamma bandwidth, and in fact there was emission of gravitational wave, and after a few seconds there was an emission of a gamma ray burst, and then an emission of ultraviolet, optical, infrared, X-ray, and radio electromagnetic radiation on different time scales. So we could follow all the evolution, and that was very important and that was very interesting because, for example, one aspect of this search is that we could understand where the heavy elements are formed in our universe. We know gold, platinum, they exist, but where do they originate from? Where? Because a star can build heavy elements, we said at the beginning, but up to iron. Inside a single star, the nuclear reactions cannot produce elements heavier than iron. So where does gold come from? Where does platinum come from? Well, in this process, when you have the 2 objects that accelerate so much, as we have seen before. And they merge. You can imagine in that region how dense matter can be. And you can imagine all the nuclear reactions that can take place. And in fact, this is the case in a kilonova. In a kilonova process, you have the so-called R processes, where R stands for rapid. And in practice, there is the environmental condition to build heavy elements. And you have the nucleosynthesis of heavy nuclei. And in that region of the space, gold and platinum have been formed. During this process, during this single event, we had the formation of the equivalent in mass, in gold, the equivalent in mass of 10 times the Earth. So 10 Earths in mass of gold were produced and thrown away in the universe. So you understand, that was really a unique outcome of our observation. We didn't know, we could not explain the abundances of heavy elements before. We know some of them can be formed in the supernova explosions, because this is another violent process. But the supernovae alone could not explain the abundances of heavy elements. Now we know mergers of binary systems made on neutron stars, they are the fabrics of gold, of platinum, lead. Okay, and this is what I have already told you. And so we are at the end of our story. Now, if you have questions, please feel free to ask. We are, say, very, very glad of this result. It involved the work of thousands of scientists, physicists, engineers, students, technicians, working all together for tens of years to build these instruments. So it was an example, as I said, of cooperation, scientific cooperation. Science, this science needs people to collaborate. We cannot make this big science without cooperation. And that was the beginning of the gravitational wave astronomy, a new tool to explore the universe. We are at the beginning of a new era. We will discover, I'm sure, more and more in the future. And so maybe you will hear more in the forthcoming years. Thanks so much for your attention. So, if you have questions, there is a microphone. Please